After we have learned about the linear least square, the problem definition, how to solve it, we learn about weighted least square. We see some numerical examples. In this video clip, as part of the chapter of linear least square, we would like to analyze some statistical property of the least square estimator. So in order to do so, we need to make some assumption. We need to explain about the framework setting. Okay. First of all, I would like to mention that a linear least square, a linear regression is actually a special case of a general regression model. A problem in a regression is you want to explain the output variable y using some information about x or the input variables, the predictors. In a general form, we assume that your y, okay, can be described by a conditional mean of y given x plus some noise. Recall that when we have assumption that, okay, your y is the output, your x is the input, and your input helps, explain the response, that is the same as believing that your y and x are some variables here can be randoms that has the joint distribution. Okay, so it has joint distribution because your x has some influence. Using information of x can help you to explain y. Okay, so when you have joint distribution between y and x, okay, and when x is given, all right, the best way to estimate y is to use the conditional mean of y given x. We will see this result when we talk about statistical estimation, but as of now, you can just take this as a as a statement. We all know that the conditional mean of y given x is a function of x. Is a function of the given random variable, and is also generally nonlinear function of x. How we can get this? Let me recall that, okay, to get a conditional mean, you need to know the joint distribution of y given x. You need to know the conditional density function of y given x. Okay, so when you derive it, it's generally nonlinear. So the least square framework is just a special case when you assume that the conditional mean of y given x is linear in x. In that case, okay, now in our subsequent analysis, we will have the assumption that your y is generated from this equation in the yellow box. You have assumed that your y is actually a linear function in x, but because there's some noise, some uncertainty, ei corrupted at at the observation, and that makes yi random, and that's why you need to perform an estimation in order to estimate beta. N, big N, is the number of samples. We will refer to this box as data generating process, because we assume that your response y is actually comes from this equation. Okay, and we will also assume some statistical property of the noise. As of now, we say that, okay, assume to have zero mean. All right, so the problem is, okay, when you have the response y, we solve beta using the LS framework. And then what can we say about beta hat? I would like to split the analysis into two cases, okay, based on the regressor matrix. In the first case, the regressor matrix is deterministic. In this setting, the vector UE is zero mean and the covariance matrix sigma. Let me recall that in the data generating process, when I write this equation with the index I try to represent it that, okay, you will have n sample, n observations. But a lot of times I would also use the vector form, which means I'm gonna stack all these observations into vectors. All right, and then that is our vector notation. So I'm gonna switch these two forms all the times. Okay. Now we say that in this slide we're gonna assume that the covariance of E is sigma, and sigma is as of now it's just any positive definite metric because it represents covariance. In the setting, we solve beta hat from least square, and we assume that X is deterministic. The important results of this one is to say that when noise is zero mean, your beta LS is unbiased estimate. That's number one result. Number two result says that, okay, we can derive the covariance by this formula. So now let's see number one. When we say unbiased estimate, it means that your beta hat, which is clearly random, if you look at the expression of beta hat, it is random because your y is on the measurements. It's from the measurement of this equation. When your noise E is random, this is the beta. Here is the true parameter. Your x is not random, it's deterministic, but because of this corrupting term, your y is random. So you would think that, okay, my beta hat is a random variable. Every time we have new data set, okay, we have data set 1, your beta hat is this value. You change the data set, your beta hat is another value. Then we are interested in the question that, okay, if I take the ensemble mean of my estimator, is it the same as the true parameter or not? If this identity holds for any kind of estimator, we call estimator unbiased. Okay, now let's explore the first property. We use the expression of beta hat now. So we take expectation of this guy. All right. As I mentioned previously, that when you take expectation, you must look at the randomness inside the bracket. What is the quantity that is random in the bracket? Napat?
Y.
Y. All right. Now, but because and with the assumption that your X is deterministic, which means City Park.
We can get x out of expectation.
Yes, okay, because it's deterministic. You can just put it outside, right? And then what is EY? EY is going to be what? Now, that's why we need the assumption. That's why we need to assume that, okay, how your data is generated. Now I'm going to use the information from the DTP. This is the equation of your measurement Y. You assume it to generate from this equation. All right. Okay, what is the expectation of X beta? Ping, can you characterize this? Expectation of X beta plus E is?
H. Expectation of beta plus expectation of E.
Plus expectation of
E.
E. Is beta random?
Yes. Wait. Not random. E is random.
Okay. So beta, we assume it to be a true parameter, right? Some unknown, but is deterministic. Okay. Then So if you multiply the whole thing, what is the expectation of E? Kanatat? Kanatat is here. Kanatat. Kanatat is not here. Expectation of E is 0. Huh? Okay, too late. You're too slow. Okay. Okay. Kanatat, can you multiply everything? The first term is Kanatat.
It's gonna be S. Square.
What do you mean square? Can you multiply this? Just multiply this guy. It turns out to be this, and then it equals to okay, switch to Totok. Totok, what is it?
I multiple by beta.
Yes, it's identity matrix, right? So it's beta at the end.
Yeah.
What are we doing? We compute the expectation of beta hat, and the key result is that because the noise has 0 mean, all right, it turns out that the expectation of beta hat is equal to beta, and that shows beta is unbiased. All right, that's the first one. I would like to remind that unbiasedness of estimator is a very standard elementary. It's like a minimum requirement that you want your estimator to satisfy. So because what happens if your estimator is biased, it means that you take the average and somehow it could be deviated from the two parameter. That's not true, right? So beta is here. It means that, okay, when you perform using one data set, this is your beta hat, right? Another data set, another realization, your beta hat would be just this blue dot, right? But in average, if you take the average of the blue dot, when it is the same as beta, that is desirable. Okay, unbiased property. Next, we're gonna take a look at the covariance of beta hat. Can someone suggest why do we care about the covariance? Napat? What can the covariance matrix tell us? Napat?
I think it's tell the dependence between input variables.
Input variable? No, this is the covariance of beta hat, not the covariance of X.
Dependence between beta variable.
Okay, that's the information you can obtain
Like
as well.
how beta 1 relate to beta 2 and relate to authors.
Yes. That can the covariance can provide that information as well. But I mean, before that, I mean the elementary interpretation of the covariance matrix is, of course, if your beta hat has n by 1, your covariance of beta hat is going to be a matrix of what size? Ping. What is the size of beta hat if your beta is n by 1? Ping.
Beta n by 1. It's n by 1.
Covariance matrix. Covariance is going to be n by n. Okay. If you are not, again, if you're behind this topic, you should review. This is in the review of, stochastic process, because I have talked about random vectors there in the slide. Covariance of beta hat, covariance of vector of n by 1 is going to be a matrix of n by n. Okay. What does it say in the diagonal terms? Total?
Equal to beta hat square.
The diagonal term equals to beta hat square.
Yeah.
Covariance. This is not beta hat square. The I elements of the covariance gives you the information about the variance of beta I. Variance. So basically, the covariance matrix gives you, just like the variance, can tell you how can you rely, how much reliable of your beta hat is, based on that that point estimate. Okay, so if the covariance is big, what does it mean? Park. If the variance is big, I mean, what does it mean in beta hat?
The data set is very varied.
Yes, highly varied. And is that a good thing of the estimator in terms of that? Okay, your beta hat is random. We all know. But of course, in practice, of course, we're gonna get some beta hat, right, from the data set. Oh, your beta hat is like 2.5. But then, as we will show you in this slide, that we can also calculate the variance of beta hat. So beta hat is 100, for example, variance. Variance is very high. It means that, okay, how much you can believe or rely on the point estimate that beta hat is 2.5? It means that when you use another data set, it also happens that oh, your beta hat may be not 2.5. It can be some other values because the variance is very high. So having covariance matrix can be an indicator on how we can trust the point estimate based on a single data set. So in conclusion, the bigger the covariance, the less reliable on the estimator. Now we're gonna derive the covariance matrix of beta. So someone remind me the definition of the covariance. Napat, what is the definition?
Is expectation of beta hat minus mean of beta hat.
Okay, all right, and
square.
Beta is vector.
Okay, transpose.
Okay, it's self-transpose, right?
Yes.
Okay, now I'm gonna explore the deviation term first. Okay, I'm gonna explore this term. Your beta hat by this expression is x transpose x inverse x transpose y, right? I give from this expression minus the mean. What was the mean we just calculated? What was the mean, Kanatat? Kanatat? No? Totok, what was the mean of beta?
Mean of beta hat equal to beta.
Equal to beta, all right? Now I'm gonna keep doing that, but now of course, then now I need to use the information about y, right? I'm going to use information that my y is from the data generating process. Okay, and then you just expand the calculation. City Park, can you reduce this quantity? What do you get?
Okay, distribute first term is beta.
Okay, the second term.
Beta plus x transpose x inverse x transpose e and minus beta.
And minus beta. Okay, great. And you will see that the first and the last term are cancelled out. All right. Now, okay, first, and then when I say covariance of beta hat, is it the same as the covariance of beta hat minus e beta hat? Are they the same, left and right? I calculate the covariance of this quantity, the left-hand side, and versus the covariance of beta hat after the mean was removed. Are they the same thing? City Park, are they the same thing?
Yes.
They are the same thing, right? No?
No.
Huh? Yes or no? They are the same because what? Because I mean this quantity on the right hand side is now having a zero mean. Look at the expression. Okay, review. Maybe you need to review. The thing is they are the same, right? Covariance of variable x and the covariance of variable x minus its mean. They are the same. Just take a look at the definition, because when you compute the covariance of some random, you need to take care of the mean, right? You need to remove the mean, but if you already remove the mean of that variable, you compute the covariance, it would be the same thing. Okay, this is very minor. I let you review after this. Okay, now you put this in the expression. So the covariance of beta hat is going to be the covariance of x transpose x inverse x transpose e. Okay, we assume our x is deterministic, so the only thing that is random in this quantity is e. Okay, now we take a look at this as what? This is simply some affine transformation A on the E. You know, this blue term is simply deterministic. So what was the result? Covariance of some matrix times E total. You have E as a random variable, but now you would like to compute covariance of AE total. What was the result? What is the result?
A multiplied by covariance of E.
Yes. Just that.
Wait.
Napat.
A square, the covariance of
It is matrix. Everything is matrix now. If A is scalar, of course it's A square, right? But that's scalar case. This is vector.
is AA transpose.
No, not AA transpose. Ping. Ping.
I don't know.
City Park.
A square.
Yes, it's A square if everything is scalar. I think I mentioned this, okay, y equal ax plus b. This is called F5 transformation, right? The mean of y is going to be the mean a times mean of x times plus b. What about the covariance of y? F5 transformation of random variable. The mean and the covariance will be related, okay? Is A covariance of X A transpose? Okay, please review. So in here, it's going to be A times covariance of E times A transpose. Okay. Now, can you put A back? A, which is the matrix. Okay, now I'm going to do it. X transpose X, inverse X transpose, covariance of E, which is sigma. And then A transpose, which is X, X transpose X inverse. And that gives us the results, the main results of this slide. Covariance of beta. First, look at this. It depends on the regressor matrix X. It also depends on the covariance of noise. So roughly, if the variance of noise is high, what happened? If the covariance of noise, which is sigma, is high, you think about, oh, big variant, big covariance matrix. Of course, can you rely on the measurements? Y? Y is going to be highly fluctuated, right? But your least square estimate, remember that it is an F5 transformation on Y. So your beta hat is also highly fluctuated from the results of Y, but which is also from the results of the noise. And that's why the covariance of beta is proportional to, you know, the covariance of the noise. We also have some observation that, oh, the regressor matrix X plays a role in the covariance in this way, which means that if in your application you're the one who can manipulate, you can decide what the regressor matrix would be, it is possible that you can pick X that the covariance is small. Because it happens that, okay, you have the sensor Y1, Y2. I mean, this is the observations, right? But then your sensor, I mean, the value in the sensor matrix, maybe it can depend on the location of sensor. It can depend on the distance of the sensor to the measurement. So maybe it's hard to explain now, but I have some problems in application that illustrate this property. That somehow in some application you're the one who can decide the matrix X. So in that case, if you have that choice, you want to design X such that the whole matrix is small, because that can reduce the uncertainty in your estimator. Now let's talk about some special case. When sigma reduces to several cases, okay, one special case is that sigma is diagonal. It's diagonal, but the diagonal elements are still different. Remember the covariance of E. Your E is E1, E2, En. So the covariance of E is going to be a matrix of n by n, right? So if it has a diagonal structure, it means that the covariance of EI, EJ, which is sigma ij, is 0 in this case. When the covariance of EI and EJ is 0, what do we say? What does it mean? Pink? Ping?
What do you mean by this?
What is the interpretation when the covariance, when the cross covariance between EI and EJ is 0?
It means that it has the same different. Yeah, it has the same different variant. Right?
I mean, what you say contradict yourself. What does it mean? The same, different? Is it going to be the same or different? What is the term in terms of statistic when the covariance, when the cross covariance is 0? Napat?
They are uncorrelated.
Yes, the samples of noise at entry I and entry J are uncorrelated. And recall that this is the sample index, right? 1, 2, 3, n. Think about how you observe samples from the sensor. So index I, it means that, okay, you observe the data from one instance, maybe one time, maybe today. The second index may be that, okay, you observe the data, tomorrow, on the second day, and so on. It's just the different instance, different realizations of the noise. So when they are uncorrelated, it means that all the samples are drawn without having some effect on each other. Okay, but then what is the interpretation of the diagonal term? Of course, that is the variance of EI that is given by sigma I square. Now we assume it to be different, sigma 1 squared dot sigma n squared. It means that as you draw the samples from each instance, the noise characteristics are not the same. It can be from the sensor. You know that you can calibrate the sensor, and maybe the scaling in the sensor will be changed, and that gives you different variance across the samples. Okay, that is the first case. That is the first in the first bullet, all right, because the noise variance are not the same. Okay, in statistics we use the term heteroscedastic assumption on the noise. Hetero mean different. All right. In the second case, which is much simpler, you assume that all the variants are constant, sigma square. So you can reduce it. You can represent sigma as the sigma square I. So it's going to be a multiple of identity matrix. In that case, we call that all the noise has homoscedastic property. Homo means something uniform, something that are the same. In that case, EI has uniform variance. In terms of sensor, like we use E that represent noise from the sensor. So if E has uniform variance, it means that the sensor perform the same way. You haven't calibrated anything. It produce the same, statistical property. Okay, let's take a look at the second case, which is assumed most of the time. When sigma equals identity, sigma square I, you would see that you can put sigma square, right? And that gives you the results that some of them will be cancelled out, and it reduces to sigma square X transpose X inverse. This is the result, of course, let me mention again, for homoscedasticity assumption on the noise in the DGP. This is a term that most of the library package on the ordinary least square give it to you. For example, the fit-lm command that I just showed, that you can also retrieve the covariance of beta hat numerically as well, and that is the expression they use. You may have question that what is sigma square? Because sigma square is the noise variance. Of course, we don't know, right? Noise is something we don't know. We just have some assumption. Does zero mean? In practice, of course, you're gonna estimate sigma square. And the way you estimate it is that, okay, you're gonna take the summation of yi minus yi hat, take the square, and then you're gonna normalize it by the number of data points. But in statistic, there's gonna be some reason that you're gonna normalize by the number of observations, subtract by the number of predictors. Okay, so this is just normalized to prove some property about the unbiased of your sigma hat square. So when you plug it back in here in this formula, that is the estimate of the covariance of beta hat in most of the software package. Last, I would like to mention this property that here it also gives us the same interpretation, that the covariance of your estimator depends on two things, depends on the noise variant and depends on the sensor matrix X. If I partition my X, the sensor matrix as X1 transpose, X2 transpose, Xn transpose, I partition it into rows. Okay, X transpose X would be X1, X2, Xn times X1 transpose, X2 transpose, Xn transpose. Okay, can you calculate this? X transpose X, Sitipak, multiply, can you multiply this?
X1 transpose,
and then
X1 X2 transpose, X1 X3 transpose.
No. Think about it. I mean, take a look at this as it looks like a row vector multiplied with the column vector.
Is the two norm square?
No. I mean, both of them are matrices, but I represent it into like partitions of row, partition of columns. So when you multiply it, you can think of this as so you can think of this as multiplication of two vectors.
Is X1 transpose,
Yes,
plus X2 transpose,
right. Okay.
until X1 Xn.
But X1 transpose is not a scalar, because X1 is a vector, right? X1 transpose is this. So this is the sum of outer products. It's a matrix. Okay. All right. Now I would like to mention that if n increases, what happened to this term? You're going to have more terms, right? And in another word, I can write this as xi transpose, I from 1 to n. If n increase, you have more terms in the summation. Is this matrix bigger? Bigger in the sense of matrix. Yes, right? Because if I use if I use n plus 1 data points, I can also write it into this, right? Plus xn plus 1 transpose. Everyone see this? So x transpose x based on n plus 1 data point can always be decomposed as x transpose x using n data point plus some other term, but that other term is also non-negative, right? So it means that x transpose x is bigger when data increases, okay, the inverse is going to be less. Okay, maybe I explain this. A equals B plus C. All of them are positive definite matrix, right? Clearly from the expression. But because A is B plus something non-negative, we can say that A is bigger than B. Napat, do you agree?
Yes, I agree.
Okay, when A is bigger than B in a matrix sense, we have the results that if both of them are invertible, A inverse is going to be less than B inverse. 4 bigger than 1, so 1/4 is less than 1. Just like the scalar case. Which means when you have more data points, the A term, when you take the inverse, it's going to be less. It's going to be less. Less in the matrix sense. Which means when you have data points, this term is less, and that gives you a smaller covariance matrix in beta hat. Which is desirable. Is it good to have smaller covariance? Total?
Yes.
Yes, right? So last conclusion, should we use more data or should we use smaller amount of data in order to get a better estimate, Total?
Higher data make higher best
Higher number of data.
number of data. Yes.
Okay. I mean, if we have, does it make sense in terms of, you know, statistical learning? It is a very intuitive, right? You should exploit all the data set that you have. And it shows here mathematically that when you use more data, the covariance of your beta hat is less. We didn't, I mean, of course, this is different point of view from computational issues. Like people in, if you use complex model, training the model, which is the same as estimating the model, is going to have some computational issues because it's going to take more time in the estimation process. But that's the issue of computation. You shouldn't use that issue as a barrier to say that, oh, I shouldn't use all the data. I shouldn't use all the data because it's going to take a long time in training process. Because that's an issue in the computation. You should be aware that as I use more data, I'm going to get a better estimate. But of course, I have some concern about, you know, the training process. So you need to trade off that point of views. Okay, I would like to again end the videos here. This is the analysis of least square estimate in the deterministic case. Okay, we have derived the covariance. At the end, the only message you should take is unbiased, and the covariance is given by this.